Ngalakin Khadijan Nyunga Boja.
He said, yeah, I have it. Join.
Oh, yeah.
Yeah.
Okay. Yeah.
Is that you?
Yeah, I can see you.
Yeah, screen.
It is.
So you can see me?
Yeah, I can see.
Can you hear me as well?
Let me try. I
Ish. Hello everyone, can you hear me? All right, that's great. Okay. Hello everyone. Let's start this lecture. Now Lujin, I understand that Lujin has started this chapter on transmission line modeling, and he has so far discussed the short length transmission line, model for the short length transmission line, and model for the medium length transmission line. Now, those models for short and medium length transmission lines are expressed in terms of two-port network, right? Is expressed in terms of a two-port network. So, what is a two-port network? I'm sure he has talked about it, but just to recap, basically you are expressing the characteristics of this network using a matrix. So as you can see, this two-port network, has two ports, the input and the output. In this case, we are utilizing the sending end as the input port and the receiving end as the output port, right? And when we represent this as a two-port network in terms of a matrix, we are interested to know the sending end voltage and the sending end current. So those are two parameters that we are interested in. And those two parameters are related to the receiving end voltage and receiving end current. So sending end and the receiving end are the two ports. So the sending end voltage and sending end current is related to the receiving end voltage and receiving end current through this matrix. ABCD matrix, right? So once we have a model for the transmission line and we want to express in terms of a two-port network, we need to know what those values for A, B, C, and D. So as long as we know the values of A, B, C, and D, we know the mathematical model for the transmission line. May it be a short transmission line, short length transmission line, a medium length transmission line, or a long transmission line. So a long transmission line is what we're going to be discussing today. Now for a short length transmission line, the values of A, B, C, D he may have derived the values of A, B, C, D are A is 1, B is Z, Z is 0, and D is 1. And what is Z? Z is the series impedance of the line, which is the resistance of the line and the reactance of the line, right? R plus JX, right? So once we know this A, B, C, D, and we know the receiving end voltage and the receiving end current, by multiplying the ABCD matrix with VR and IR in a column vector, we can find this Vs and Is, which is the sending end voltage and the sending end current, right? So that's fairly straightforward. Now for a medium length transmission line, because a short length transmission line is essentially just a series impedance, right? Series impedance R plus JX. A medium length transmission line is a pi model. So you still have that series impedance on the horizontal. You can see in the pi R plus JX. X is omega L because it's inductive line. And also you have two capacitors on either side of the line. One on the sending end and the other one on the receiving end, two shunt capacitors, right? So again, by doing basic circuit analysis using Kirchhoff's voltage law, Kirchhoff's current law, we can obtain matrices ABCD, values for ABCD, and the values for ABCD is going to be ZY on 2 plus 1, that will be the value for A. Value for A, B can be derived, which is simply Z. Then value for C and value for D can be derived as well. They are in terms of Z and Y. And we know what Z and Y are. Z is the series impedance on the pi, and Y is admittance, right? Because Y on 2 on either side. So once we know these ABCD, again, if you know the receiving end voltage and receiving end current, we can obtain the sending end voltage and sending end current. That's the whole idea. It's relating those voltages and currents on the sending end and the receiving end through the ABCD two-port network representation. Okay, now, so again here, these are some ABCD matrices for different types of circuits, right? It's easy, you can derive those ABCD values. You can see on the first row, we have the model for the short transmission line, which is simply a series impedance. Then we have a bunch of other networks, and also we see here on the second last row, the model for the medium length transmission line, which is a pi circuit, and we also can see the ABCD values for that pi circuit in the two-port network representation. Now let's say, well, this is also fairly important. Let's say you have two circuits connected in series, right? Two circuits connected in series, and you have the two-port network representation for both of those circuits, right? In other words, the values of A, B, C, D for the two circuits. You can, to obtain the overall ABCD model for that, you can simply multiply the two matrices together. That's what that last row is suggesting, right? It's kind of a convenient way to actually find the sending end voltage and current when you know the receiving end voltages and currents, right? Okay. So you have seen the medium length transmission line, so I assume that Lujin has gone through this. So what we need to cover in this lecture to complete this section is the long transmission lines. Now the long transmission lines, lump parameters are no longer sufficiently accurate. So for the short transmission line and the medium transmission line, we are modeling using lump parameters, right? We have capacitors on either side, we have a series impedance, so we're using lump parameters. Now if we are talking about long transmission line, this lump parameter model is no longer sufficient, right? So the shunt capacitance and series impedance must be treated as distributed quantities. We need to treat it as a distributed quantity, which means we might now have to involve differential equations to do the model. Because we need to perhaps take a small section of the line and then represent that using lump parameters and then write some differential equation to come up with a model. You're going to see that. So the shunt capacitance series impedance must be treated as distributed quantities, and the voltage currents on the line must be found by solving differential equations of the transmission line. So that's what we need to do. Now the line constants R, L, and C are given as per length values. So R, remember R, X, and Y, R inductance and the capacitance, they were per length, per meter, right? Again, we still have those values. Having units of R has to be resistance per meter. I don't know what that W is. So ohms per meter. H is henries per meter, and L is henries per meter, and C as farads per meter. They are uniformly distributed along the length of the line, so that will be our assumption. In order to account for the distributed nature of the transmission line constants, we can consider the circuit shown here. So here is like looking at a section of that long transmission line. So you can see the receiving end. Let's say receiving end is at point X, right? X from the very end of the transmission line, from the receiving end, right? We come some distance X, and that's the point that you see on the right, right? And then we have the series impedance on the horizontal line on the pi circuit, right? We see that. So we have a resistor and we have an inductor there, right? Resistor and inductor. So let me show that. So this is the resistor and the inductor we are looking at, right? And then we have the capacitor, the shunt capacitor, which is this term here, right? Shunt capacitor. Now, this Z here is the impedance per meter. Impedance per meter. So we are now considering a distance delta x. We're considering a small distance delta x. So x on the right hand side, x plus delta x on the left hand side. So we have x equal to 0 at the receiving end. We have come some distance x, right? And then we are looking at this section going from x to x plus delta x from right to left. Okay? So Z is the impedance per meter. So if you are now considering a short distance delta x, that Z has to be multiplied by delta x, because that's the distance that we are considering, right? So you have, for the impedance on the horizontal line, we have Z times delta x. Again, the shunt capacitance is Y. Again, we need to multiply that by delta x. Why? Because we are considering a small section delta x, right? Y is actually the admittance per meter. So we need to multiply by delta x. So you can clearly see why we are multiplying by delta x. Now we have also included a resistor, which is that vertical resistor highlighted in red, and we haven't seen that in the previous models before, right? In the pi model, we had two capacitors on either side. We didn't have a resistor. So this resistance value is high that we can neglect it. So we can ignore it. So when I write the equations now, we're going to ignore it. Although this picture shows that, we're going to ignore that. Right? We're going to ignore that. All right. So what else we are marking here? So the current, right? The current that flows on that line is Ix, right? Because that's the current that's flowing into point X. Current that is flowing here is Ix plus delta x, because we are talking about the point x plus delta x there, right? Yeah, so that's all. That's and the voltage on the right, because we're considering point x, it's Vx, and the voltage on the left, we are considering the point x plus delta x, so it's the voltage at that point is Vx plus delta x, right? So the notation is consistent here, and it follows along the discussion from the previous lecture, okay? All right, so let's continue on. So Z is some resistor value plus j omega L. Y is j omega C, right? We usually neglect G. G is neglected because that resistor value is quite large, and we can therefore ignore the conductance. Conductance is the inverse of the resistance, right? So we can now write Kirchhoff's voltage law equations, right? So here we can say that Vx plus delta x, which is the voltage on the left-hand side, must equal Vx, which is the voltage on the right-hand side, plus the drop across the series impedance. So the drop across the series impedance is simply the current, Ix, multiplied by the impedance. Impedance is simply Z delta x. So that's very straightforward. And then you can take in that equation Vx into the left-hand side. So you have Vx plus delta x minus Vx. Delta x on the right-hand side, you can bring it across, right, to the denominator on the left-hand side. So now you have Vx plus delta x minus Vx on delta x is equal to Zix. And we know as the limit delta x approaches 0, that left-hand side is simply dV dx. Right? That's the definition of the derivative. So we can rewrite this equation, right, that we wrote using Kirchhoff's voltage law, right? A very simple equation. Dv dx is Zix. We could write that, right? That's the first equation. So here again, this is the same equation that we derived in the previous slide. Dv dx equals Zix. Now that's applying Kirchhoff's voltage law. We can apply Kirchhoff's current law, and we can say that current Ix plus delta x on that branch, on the horizontal branch on the left, right, on the top, that must equal the current Ix, right, which is flowing out of that first node, right, plus the current that flows in the shunt through the capacitor, through the shunt capacitor. And the current that flows through the shunt capacitor has to be, well, the admittance value, which is Y delta x times the voltage, right? So the times the voltage, what is the voltage that appears across that? Vx plus delta x, right? Vx plus delta x. So you have that equation, Ix plus delta x must equal Ix plus Y delta x multiplied by Vx plus delta V, right? Voltage times admittance is the current, right? So now again, Ix on the right-hand side can be brought to the left-hand side. So it becomes Ix plus delta x minus Ix. Delta x can be brought across, so into the denominator on the left-hand side. So you have that expression, right? And if you set if you set the limit of delta x to approach 0, then you know that left-hand side is simply di dx. Di dx must equal yvx, right? So we have two equations, right? We have two unknowns. The two unknowns are V, right, which is the voltage, and I, the current, right? So Vx and Ix are the unknowns, and we have two differential equations. We have written two differential equations to solve that. Right. So here are the two differential equations that we got that I highlighted in red and yellow on the top left, right? On the top left. So if I now want to, we know there are two unknowns and two equations that we have written, right? And we want to eliminate one variable. So let's say I want to eliminate the current. What I can do is I can take the first equation, which I highlighted in red, dv dx equals zix. I can differentiate again. So if I differentiate dv dx with respect to x again, you get d squared vx dx squared is z. On the right hand side, we need to differentiate with respect to x. So you get di dx, right? Di dx. And from the second equation that I highlighted in yellow, we know di dx is actually y times vx. So we can substitute for that. And if you substitute for that, then we have d squared v dx squared must equal zy vx. Right? Very straightforward. Right? We have that equation. So that equation, or everything is in terms of one variable, which is vx. Right? So we can then, we have the second order differential equation, right? Z and y, what are Z and y? Z and y are series impedance per meter, right? What is y? The shunt admittance per meter, right? And those are values that we know, a characteristic of the transmission line. We know that. That will be available from a data sheet. So we can now write the characteristic equation. To solve this differential equation, we can write the characteristic equation. Right? So how do we write the characteristic equation? If we have the second derivative of a variable, we replace that with lambda squared. I mean, it can be lambda, it can be any variable, right? Any symbol that you want to choose, right? So we replace the second derivative with lambda squared, first derivative with lambda, right? There is no first derivative here. And if you're not differentiating the variable, then it's lambda raised to the power 0, which is 1, right? So the characteristic equation for this differential equation then turns out to be lambda squared minus zy, right, equal to 0, right? So the values of lambda are then plus or minus square root zy, right? Zy are constants, some constants, right? So the square root of that, right? So Z is, what is Z? Z is the series impedance per meter. Y is the admittance per meter, right? So, so if I use the same notation as before, this value here, this gamma is actually lambda, right? This is lambda, right? You use gamma in the characteristic equation if you want. It doesn't matter. It's the same thing, right? Okay, and that gamma is square root zy. I mean, rewrite the characteristic equation with gamma, then nothing changes, right? I wrote lambda squared. Doesn't matter. So that's it. Gamma is square root zy. That comes from our previous slide. So what is the solution? That solution is that Vx is some constant times e raised to the power gamma x, right? Plus a2 e raised to the power minus gamma x, because we have two solutions. Those two solutions are plus value and the minus value, right? Yeah. So how do you find A1 and A2? We obviously have to use the initial conditions, right? Like any other differential equation, we have to use the initial conditions. Now, if I take the expression for Vx, and if I differentiate once, then we'll get gamma A1 e to the gamma x minus gamma A2 e to the minus gamma x. And we know that is equal to Zix, right? We have seen that equation. We know is Z to the Ix. So Ix can therefore have this expression. That's Ix. That's Ix. And ZC, I mean, if you do the simplification, you can see that ZC, in fact, is square root Z on Y. It's very straightforward, right? So what are we looking at here? We have the expression for Vx. Vx is in terms of gamma, right? And we know what gamma is because gamma is related to yn is z, lowercase yn is z, which we know, right? And a1 and a2 are constants which we can determine if you know the initial conditions, right? In other words, when x equal to 0, what is the voltage, right? If you know some initial conditions, yeah. If when x equal to 0, what is v dot, right? Those are the initial conditions, right? If you know the initial conditions, we can determine a1 and a2. Because remember, v dot is related to I current, right? So it's V0 and I0, it's related. Those are the initial conditions, right? So, so we have this expression, right? So, yeah, we have expression for Vx and Ix. Yes? Yeah, okay. So do you agree, you agree dV dx is that expression, right? Which I put it in a rectangle, right? Is Zix, right? So you probably then agree I is equal to that A1 e to the gamma x minus A2 e to the minus gamma x over Z on gamma. Do you agree with that? You agree with that. Okay. Right. Now, yeah. So, right. Yeah. Okay. So it's just a basic simplification. So if I substitute here square root zy here, does it turn out to be the same? No. It should be just, yeah. Because, yeah, it's the same thing. Now, here, this is Z on gamma, right? This is Z on gamma. And what is gamma? Yeah, if you substitute for gamma, then you will end up with this expression. If you substitute for gamma, you will end up with that expression. Yeah. Because gamma is in terms of Z and Y. So if you substitute for that, you will end up. It's fairly straightforward. Yeah, thank you. Okay. So we can give ZC a name, right? We can give it a name. Doesn't harm to give it a name. Z is called the characteristic impedance, right? Okay. So then we have these initial conditions. V0, let's call it VR. I0, let's call it IR, right? V0 and I0. So we can now use those initial conditions to find what is A1 and A2. So if I take the first equation, Vx is that. If I substitute x equal to 0, then I have on the right hand side A1 plus A2, right? And that must equal VR. That is my initial condition, right? And I can do the same because I have an expression for Ix, right? I can find what is I0, right? Then I0 is I1 minus I2 on Z, right? And that is IR. That's my initial condition. So you have two unknowns, A1 and A2, and you can solve for them. And if you solve for A1 and A2 in terms of VR, IR, which are initial conditions, and ZC, something that we know, characteristic impedance, we get this for A1 and A2. I mean, a simple solution which you can do, right? You get that for A1 and A2, right? So what is now the expression for Vx? Vx is simply A1, which is this term here, right? We have solved for A1, e to the gamma x plus A2. Again, we know what A2 is in terms of our initial conditions, e to the minus gamma x. And we can make the same substitutions for Ix, right, for A1 and A2, and we have those expressions. And now, in those expressions, we can group the VR terms and the IR terms. We can group them. Yeah? Instead of grouping the exponentials, we can group the VR and the IR terms. If you group the VR and IR terms, then we end up with this expression. Simple manipulation, right? Simple manipulation. Then we end up with this expression. We have grouped the VR and IR terms. We end up with that. Right? Simple manipulation. There's nothing there. Right? So now you will recognize that those terms are actually cosh and shine. Cosh and shine. Right? Because they don't have a J term there. So they are coshes and shines. Cosh and shine. So we can then write this. Therefore, that term that I highlighted is cosh gamma x. The other term is shine gamma x. Right? So those are the expressions for Vx and Ix. And in terms of gamma and ZC. Right? In terms of gamma and of course, our initial conditions, VR and IR appears in the equation. Right? They appear in the equation. Right? We have cosh terms and shine terms there. And our initial conditions and the characteristic impedance and the gamma term. Right. So, we can now, so we have this, right? So we can already see the matrix, right? Because if I can draw a matrix like this, right? Right? And if I can delete that and put that VR there, if I can delete that and put that IR there, right? I can delete that, I can delete that. So I have my ABCD matrices. Right? I have the ABCD matrices. A is cosh gamma x, B is ZC shine gamma x, B, C is 1 on ZC shine gamma x, and D is cosh gamma x. We have those values. Now, so we have, from our previous slide, we have our A, B, C, and D, right? And A and D are the same. Cosh gamma D, because if I replace x is the distance from the receiving end heading towards the sending end, right? Now, if I want to consider the entire transmission line, right, your x will be the length of the transmission line, and the length of the transmission line is D or L, whatever it is, right? So I substitute that. So cosh gamma D, now with a little bit of manipulation, you can say cosh gamma T is Z bar Y bar on 2 plus 1, where Z bar is ZC shine gamma L, right? It's not sine, it should be shine. There's the H missing there, right? Which is also Z shine gamma L over gamma L. L is D, right? L. See, we're using L and D somewhere. I should have used the same letter. So notice that L and D are the same thing, right? L and D are the same thing. Should have used the one letter, but I have to correct that typo. But L and D is the same. Right? L and D is the same. Now, you can, given that expression for Z dash and Y dash, you can multiply them together, simplify it, and figure out that it's actually cosh gamma D. Not going to do that, right? It's just a simple exercise, trig exercise, right? You can do. Now, there is a reason why it's been written like that. Because for the medium length transmission line, A and D were equal to Z, Y on 2 plus 1, right? So this is also written in the same form, right? And B was Z for the medium length transmission line, right? So here, B is Z dash. C for the medium length transmission line was Y times YZ on 4 plus 1, right? So go for ABCD matrices for the long length transmission line. What we've done is actually we changed the Z and Y to Z dash and Y dash. So we just modified it. Z and Y, we modified it. Otherwise, the form is the same, right? So how do we modify Z and Y? Well, those expressions on the right says how to modify it. Z dash is you take the Z, right? And you multiply that by sine gamma L over gamma L, right? So that's how you modify Z so that it becomes Z dash. How do you modify Y so that you get Y dash? You take Y and you multiply by tanh gamma D on 2 over gamma D on 2. So you modify it. But then the form is exactly the same as the medium length transmission lines. Right? That's it. But you understand the whole derivation. I mean, even expressing A equal to cos gamma D, expressing that as Z dash Y dash on 2 plus 1, right? Just try it out at home if you have some time. Right? Just yeah. Try it out. So that's it. So here, long transmission line model, right? We are representing using ABCD matrices in a two-port network. A, B, C, and D are according to these expressions. You simply get Y dash by modifying Y, you get Z dash by modifying Z, and if you know the receiving end voltage and receiving end current, you can find the sending end voltage and sending end current. That's it. Right? Okay, so this page here summarizes everything. Right? For short transmission line, again, you're not expected to memorize any of that. You will get a formula sheet. And the formula sheet, things will be given, all these formulas will be given to you. And you will have an idea of what the formula sheet looks like. It's perhaps already on LMS. You can check. Yeah. So when you're studying, you know how to study for this unit because it's you don't need to memorize that. It's just the understanding. You understand how to get those values, where they are coming from, just having an understanding. Yeah. So here is the short transmission line. We only have a series impedance. For medium length transmission line, we have a pi model, right? Which is described by Y on Z. For long line transmission line, again, we classify the transmission line as short, medium, and long based on the distance. If it's less than 80 kilometers, it's a short. 80 and to 240, it's a medium length transmission line. And greater than 240, it's a long transmission line. Again, the A, B, C, D matrices for the long transmission line, you can see it has the same form as the medium line, except Y and Z's been modified. And how to modify Y and Z to get Y dash and Z dash are given here in this table, right? Gamma is a constant, propagation constant, which is the square root of YZ. And uppercase Z is the lowercase z times the distance L. The D's here should be L's. It's the same thing, right? Length of the transmission line. Y is again takes the admittance and multiply per meter value multiplied by the length of the transmission line. So that's just a summary of that whole thing, right? Model for short, medium, and long transmission lines. Here are some definitions. Perhaps you already know. Sine is e to the x minus e to the minus x on 2. Cosh is e to the x plus e to the minus x on 2. We utilized that when we came up with the expressions. And then tang and cos and sine, they're all there, right? If you want to know those and want to do further derivations, all those relevant formulas are there. All right, so let's take a look at this example. You've done the same example for short transmission line, medium, and now we are looking at the long transmission line. It's the same example, right? So a 210, so that's a typo. It's not 220, it's 210 kilovolts, 150 megavolt amps. So these values, when we read, we are reading a voltage. A three-phase transmission line is 140 kilometers long. So there are some rated values. So rated voltage is 210. Rated power is 150 megavolt amps, right? So if I have the rated voltage and rated apparent power, megavolt amps is voltage times current, right? Apparent power, right? So if I have the rated voltage, if I have a rated power, I can also find the rated current. Rated power divided by rated voltage will give me rated power, rated current. Right? So these are the rated values. It's 140 kilometers long. So it's essentially a medium length transmission line, although we are going to calculate, we are going to use the long transmission line model, right? We could find all the relevant parameters using the medium length transmission line, and that will be accurate enough. But still, we are going to calculate the relevant parameters using the long transmission line, right? Model. Again, resistance, series resistance per kilometer is that many ohms. Inductance value per kilometer is that, the X value is given, right? Farads per meter. Actually, yeah. This is the X value, so it's multiplied by omega L, right? It's been multiplied by omega, so it's ohms. And then you have the Y value, right? 4.1 times 10 to the negative 6. Again, it's per unit length. The voltage at the receiving end of the transmission line is 210 kilovolts. So we know the receiving end voltage, right? So I don't see the receiving end current yet. Hasn't been stated. We know the receiving end voltage, but we know from the very beginning, if we know the receiving end voltage and receiving end current, we can find the sending end voltage and sending end current. We know that, right? Now, I'm just trying to read this question and trying to get some information out of it as I read it. So I've talked about the rated values at the beginning. And here, the receiving end, we know the value is, receiving end voltage is 210 kilovolts. This transmission line is identical to that in the short transmission line example, and is now treated as a long transmission line. That's fine. Now, so I only have the receiving end voltage. Haven't seen the receiving end current here. Anyway, doesn't matter. Let's proceed. What is modified series impedance and shunt admittance for this transmission line? Because we have the series impedance, shunt admittance, right? We have that formula to be able to calculate those, then we can modify it. We have the formula to do that as well. And because we have the R, X, and Y values, and that's all we need to be able to calculate all that. So let's have a look at that calculation first, right? Let's have a look at that calculation first. So we have the R value, lowercase r, so we can calculate the uppercase R because that's the resistance for the entire line. We simply multiplied by 140, right? Per unit resistance that was given was per kilometer. So it's 140 kilometers long. We simply multiply by 140. So we get 16.8 ohms, right? X value again per unit, per distance, per kilometer. So measurement. So we multiplied by the distance, 140. So you get that many ohms, 123.2 ohms, right? Again, we do the same thing for Y, right? The admittance, right? And then you get per unit, per kilometer value multiplied by the entire distance, we get the relevant value for Y, uppercase Y. Then now we can calculate gamma. Gamma is simply the square root square root y z. We know the lowercase y, you know the lowercase z, right? Right? You know what lowercase y and lowercase z, what those mean. You multiply those values and you have the answer to that, right? And that is a complex number, right? Because y is the admittance, right, of the capacitor. So it's J times some value, right? Because 1 on J omega is the impedance, admittance is the inverse of that. So that's why the J term is on the numerator. Yeah? So Z is made up of little r and little x, right? Little r is this value, x is that value, right? Of course, jx, right? Jx is there, right? R plus jx is the little z, which is the highlighted term. So we have gamma. So we can calculate gamma L just by multiplying by 140. So now we can find the modified Z by taking Z. Z is R plus Jx, right? Multiplied by shine gamma L on gamma L. We can find that, which turns out to be that value, right? So if you punch the numbers in the calculator, the formula, we have derived it. You have it. It's just a matter of punching it, identifying and the correct values and punching in the calculator, right? So you can obtain that Z bar. And also you can calculate Y bar. Because once you calculate Y, once you have Y, you can modify the value of Y to get Y dash because you have the relevant values in the formula, which you can punch in to obtain those values, right? So that's straightforward. So given those little r, x, and y, you can find y and z, uppercase y and z, and uppercase y dash and z dash, which is the modified values. And those calculations are there, so I recommend you try that at home, right? So what do we do next? Okay. What is the sending end voltage, right? So what we have done so far, we have found the modified Z, modified Y. In other words, for this long transmission line, we know the A, B, C, D values. Because if we know Y dash and Z dash, we know the A, B, C, D values, right? We know that. We also know VR, that is given in the question, yeah? But IR was not given to us, remember? Yeah? So let's have a look at this. What is the sending end voltage if the line is supplying rated voltage and apparent power, and the line is supplying rated voltage and apparent power. So rated voltage and rated apparent power, right? Rated voltage and rated apparent power. So if I know the line is supplying rated voltage and rated apparent power, that means it's supplying rated current, right? And I know the value of rated current. So IR, yeah? So let's read it again. What is the sending end voltage if the line is supplying rated voltage and rated apparent power at 0.85 power factor lagging? So it's supplying the rated current to the receiving end. So the receiving end current, I know the rated current. And also I know the power factor. Power factor is 0.85 lagging. So what is power factor? Power factor is the angle between the voltage and current. Receiving end voltage is given, but the phase angle was not given, but we can choose the receiving end voltage phase angle as our reference, as angle 0. Right? Because when you're talking about the power factor, what power factor are we talking? We are talking about the power factor at the receiving end and the load on the receiving end. Yeah? Do you follow me? Because it's important. So let me draw it. Right? So we have a transmission line, right? We have a transmission line. So let me draw, it's a long transmission line, so let me draw it like this. Something like that, right? So this is Z dash, this is Y dash on 2, this is Y dash on 2, right? Yeah? So now we have a load connected here at the receiving end, right? Now we've been told rated current flows here, I rated, right? Didn't say in exact those terms rated current, but it said it's providing the rated apparent power at the rated voltage, right? So the receiving end voltage is a rated voltage. This voltage here is V rated, right? And we've been told it's supplying all that at a power factor of 0.85 lagging. So when it's saying it's supplying the rated current to a load which is receiving rated, which has rated voltage across it, right? And talking about a power factor, it's talking about the power factor of the load, right? So if I now take the rated voltage at the receiving end as my reference, right? So we are talking about this power factor is the angle of the voltage minus the angle of the current, cos of that. See, when you say power factor, you need to know power factor where and what, right? So that means now rated voltage, I'm taking that as my reference, angle 0, power factor is 0.85 lagging, right? So cos inverse 0.85 will give me the angle, right? And that angle is lagging, which means the current has to be lagging the voltage, so it will be a negative value. So cos inverse 0.85 will give me a positive value, but the angle of the current is the negative of that, because voltage has an angle 0, and if it's a lagging power factor, then the current has to be lagging there, right? So cos inverse 0.85, yeah. So cos inverse 0.85 is 31.8, right? You can punch in the calculator, you will find 31.8, but since it's a lagging power factor, we need to put a negative there for the current. Current must lag the voltage. So I know the receiving end voltage, I know the receiving end current, right? I know the ABCD matrices for the long transmission line. Therefore, I can find the sending end voltage and sending end current. I'm not going to even do the calculation. Just you're convinced and you can find those values, right? You can find those values, just a matrix multiplication, right? And if you do the matrix multiplication, you're going to get this value here for the sending end voltage. 144.1, phase angle 14.9 degrees, right? Receiving end voltage was how much? Receiving end voltage was 121 angle 0. So obviously the sending end voltage has to be bigger than the receiving end voltage because there's some voltage drop in the line, right? Okay. But it's important to note that you actually chosen the receiving end voltage as your reference, Because when you do circuit analysis in first year, you would always see the phase angle 0 on the sending end, right? But you don't have to choose it like that. You can choose it anywhere you want. Anything to be the reference. So we've chosen the reference to be at the receiving end voltage. Because that makes it simpler for us to then calculate the power factor and find the angle of the current, sending end voltage, we know receiving end voltage, we know receiving end current, we know the ABCD matrices, therefore we can find the sending end voltage and the sending end current. Okay. So, what is the other question that we need to? All right, what is the voltage regulation of the transmission line for the case in B? All right, so we need to know the voltage regulation for the case in B. Right. So here it is, right? We need to know the voltage regulation. So what is voltage regulation? So what is case in B? Case in B is we are supplying the rated voltage, rated power to the load, right? Which is at the receiving end. That's what we are doing. Yeah, that's the case we are talking about. That's the scenario we are talking about. So when we now want to talk about voltage regulation, we have rated current flowing through the load. That's the scenario we are talking about. Voltage regulation is what happens to the sending, to the receiving end voltage if I now take the load off. Right? I disconnect the load. I have this scenario. The scenario is we have the sending end, right? We have a transmission line. We have a load connect to the receiving end. The voltage across the receiving end is 121 angle 0, right? And the voltage at the sending end is whatever we calculated, which is greater than 121. Whatever the calculator, I don't know the value. You know the value, right? So that's the scenario we are talking about. So voltage regulation is now I have the receiving end load, I take it out, right? What happens when I take it out? When I take it out, the voltage at the receiving end changes, right? Voltage at the receiving end, because there is no current will flow through the horizontal branch, right? So the voltage at the receiving end will then rise to what it's at the input. Yeah. Now what was at the input? What was at the sending end? At the sending end we had 200 and line to line voltage was 267, right? Phase voltage is 154. You know how to go from phase voltage to line, you simply multiply by √3. We assume it's a star connection, right? Unless otherwise stated, that's what we are going to do, right? But anyway, we have the phase voltage, which is 154. We can even work on the phase values, that's fine. And the phase value at the receiving end was 120. We can work with those numbers if you want. Or we can work with the line-to-line values, which is also fine, because they are out by the same factor anyway, right? So now the voltage is going to rise, right, from 121 phase value to 154 phase value. Yeah. So voltage regulation is defined as the no load voltage minus the full load voltage divided by full load voltage. So you know what no load voltage means. When I remove what will be the receiving end voltage is the no load voltage. Yeah. Because you need to understand what no load means. That's what no load means. Because I have the scenario where we are supplying some rated power to a load, right? And we have the rated voltage across the load. We now, from that condition, from that scenario, we have well, we have a certain sending end voltage, we just remove the load and then see what is the voltage at the receiving end. Yeah, and that's the no load voltage. So no load voltage is higher than the full load voltage. Right? So we have 267, right? That's the line to line voltage. We have 210, that's the full load voltage line to line divided by full load voltage times 100. That's the voltage regulation. So now we have to calculate the efficiency of the transmission line. So the efficiency of the transmission line is we have some power injection from the sending end, right? And we receive some power at the receiving end, right? So the efficiency of the transformer is how much power we receive compared to how much power we inject, right? If the losses in the transmission lines are less, then we have a higher efficiency, right? And for us to figure out the efficiency, we know the sending end we need to know the sending end voltage, sending end current, so that we can calculate the power injection. We need to know the receiving end voltage, receiving end current, so we can calculate the receiving end power, and then we can calculate the efficiency, right? So if you know the sending end voltage and sending end current, how do you calculate the active power injection? VI cos theta. And then you do VI cos theta at the receiving end current and receiving end voltage, and you have the active power received at the, well, the load, the receiving end. Right? So you calculate the sending end current. Again, if you know the ABCD model, you know receiving end voltage, receiving end current, you can calculate that, right? And then you can calculate the input power, power that you inject into the sending end, output power, power that you take out on the receiving end, take the ratio of P out to P in, and that's the efficiency. I'm not going through how to multiply and all that. I just want to explain the concept so that you understand, and then you can do the number crunching yourself. Yeah. So here is just some comparison values that we have got. So sending end voltage, when we use the short transmission line, was 158. When you use the medium length transmission line model, it was 154, right? But when we use the long transmission, the exact model, it's still 154. So you can see the medium length transmission line model is adequate for this because of the length of the line, 140 kilometers. You can, this demonstrates that. And same with the currents. You can see the currents we've calculated using for the medium length and the long length are more or less the same. So that extra modification required to have a more accurate model for this 100 kilometer line is not justified because we can not modify and still get the same sort of answer, right? Yeah. Okay. So I think that brings us to the end of that chapter, right? That's the end of chapter 2. Ooh, this is no good. Yeah. All right. So, yeah, that's okay. All right. So in this chapter, we're going to talk about transformers. And if you want to read a textbook, then you can read this textbook, which I've referenced here. It will be chapter 3, right, if you want to read it. So what's the table of contents? We're going to basically, followed by a brief introduction, we're going to talk about ideal transformers, a more realistic model for transformers. We're going to talk about the per unit system. We're going to talk about three-phase transformers and briefly talk about auto transformers and phase shifting transformers and tap changing transformers. Right? That's basically it. So power systems are characterized by many different voltage levels ranging from high values such as 765 kilometers down to 240, 120 volts. So from very large values to some small values, and we know those large values are near the generation sites to transmit small currents so that I squared R losses are small. And then we step it down to lower voltage values for residential and commercial use, something like 240 volts. Transformers are used to transfer power between different voltage levels. The ability to inexpensively change the voltage levels is a key advantage of AC systems over DC systems. That's one of the advantages, because in an inexpensive way, we can change the voltage values. And obviously, we use transformers to do that. Use transformers to do that. Yeah, we use transformers to adjust the voltage levels of AC power systems, but then we can use, to do something similar, we can use DC-DC converters, which you will learn if you study power electronics as an option. Power electronics, because those are power electronics devices that will allow you to convert one DC value to another DC value, or DC to AC, or AC to DC. Right? So there are converters that does that job, and if you study power electronics as an option in this course, then you will come across that. I think before we go through this chapter, maybe we can take a very short break and start around 4:15. I will run up to my office and get the power cable before the computer run out of power. Yeah? Okay. So let's take a short break. And for those of you, we'll be back shortly. If the computer runs out of power, you might have to log into Zoom again. So if you're kicked out of Zoom, please log in again, but I will go and get the cable and come back before the start of the second part of this lecture. Can I quickly run and get the cable? Because the power is going to be, yeah, and then I'll answer.
I don't know.
I will start in 5 minutes. Yeah, just giving a bit of recovery time for the computer. All right, I think we can make a start again. So let's begin our discussion with what is an ideal transformer. Right? An ideal transformer has the windings have zero resistance of an ideal transformer. We know the transformer has two windings, the primary winding and the secondary winding. And the winding resistance of an ideal transformer will take it as 0. Therefore, I squared R losses in the windings are 0. There is no resistance. If we assume that the winding resistance is 0. So, we'll also assume that in an ideal transformer, the co-permeability is infinite. We'll talk a bit more about that. Which corresponds to zero co-reluctance. So the reluctance is 0 in an ideal transformer. And we'll also assume there is no leakage flux. That is, the entire flux is confined to the core and links both windings. Because you have the primary winding, we have an energy source, an alternating current flowing through the primary winding which creates a flux, a time-varying flux, which links the secondary winding, and we will assume that the entire flux is confined to the core of the transformer. And that changing flux that links the secondary will induce an EMF according to Faraday's law. Right? Now, we'll also assume that there are no co-losses. So in an ideal transformer, we'll assume there are no co-losses. So we'll define the primary side of the transformer as the side that actually receives power from a line, and the secondary as the side that usually delivers power to a load. We just assume that. Primary is usually the side of the higher voltage, but maybe low voltage side on the generator step-up transformer. So at the generator side, we have a step-up transformer. In that case, the primary will be obviously the low voltage side. Right. So the above is a schematic representation of a single-phase transformer with two coils on a magnetic core. You can see the magnetic core that facilitate the linking of the flux from the primary to the secondary. So the two coil where the magnetic coupling is assumed to be perfect because we assume there is no leakage flux. The same flux passes through each turn of each coil. So there is no flux leakage in an ideal transformer. Right? So Faraday's law gives us the following equations. Induced EMF in the primary, N1 number of turns in the primary coil, d phi 1 dt, that's the flux linking the primary coil. Induced voltage on the secondary is N2 d phi 2 dt, right? Flux linking the secondary coil, the time derivative of that. Obviously, if we assume that there is no leakage flux, then phi 1 must equal phi 2, right? Again, Kirchhoff's voltage law, V1 is the voltage at the primary terminal, must equal the induced EMF plus some IR loss in the winding. And if we assume in the ideal transformer case, we'll assume R1 is 0. Same can be said, V2 is the voltage at the terminal of the secondary, but that must equal the induced voltage plus the current that flows in the secondary winding times a winding resistance R2. But we'll assume R2 equal to 0 in the ideal transformer case. So then we can write the terminal voltage V1 on the primary is then N1, which is the number of turns in the primary, times the time derivative of the flux. It's a common flux, right? Phi 1 is equal to phi 2 equal to phi c in the core, flux in the core. There is no leakage. And then V2 can be written as N2 d phi c dt, right? So then that leads us to if you divide these equations, right, one with the other, then we have V1 on V2 must equal N1 on N2. The flux, time derivative of the flux terms cancel out. And N1 and N2 is a lowercase a, which is also called turns ratio. Right? This is ideal transform equations. I'm sure you have seen this equation before somewhere, perhaps in year 12 physics or first year electrical engineering unit. Right. Electromagnetic relations. The magnetomotive force, which is called MMF, is calculated as the magnetic flux times the reluctance R of the circuit, right? So let's consider the circuit on the top right. You see two dots. So those two dots represent the positive potential of the coil. So where the dot is, that's the higher voltage, the positive potential. So that's why the positive is on the top for both, because the dots are on the top. Now, on the primary side, the convention is current flows into the dot. On the secondary, the convention is current flows out of the dot. That's the convention, right? So I1 flows into the dot, I2 flows out of the dot. Now, magnetomotive force, if a current is flowing, magnetomotive force is the turns ratio times the current, right? It has a sign. Now, if current flows into the dot, the magnetomotive force is positive. If current flows out of a dot, magnetomotive force is negative, right? So the magnetomotive force, the MMF, is therefore N1I1 because I1 flows into the dot, and it's negative for the secondary because I2 is flowing out of the dot, so it's minus N2I2, right? And the MMF must equal the flux in the core, phi C, times the reluctance, RC, right? Now, in an ideal transformer, the reluctance is 0, right? Infinite permeability, reluctance is 0. So that's an assumption we make. Remember, I said in the previous slide. So then we have the equation N1I1 must equal to N2I2 must equal to 0, which then gives us the equation I1 on I2 must equal the inverse of turns ratio, right? Is the inverse of the turns ratio. I1, I2 equals the inverse of the turns ratio. And we know in the previous slide we saw V1 and over V2 is actually the turns ratio. So we have this equation. V1 must equal the turns ratio times V2. We've derived that equation, right? So V1 equals A times V2. We can see in that matrix equation that's what it is. And we have I1 equal to 1 on A I2 because I1 on I2 equals the inverse of the turns ratio, right? So in the secondary, right, we have the impedance. So if you connect an impedance to the secondary terminal of the transformer, we have V2 on I2 equal to Z, or I2 equal to V2 on Z, if you connect an impedance on the secondary. So I2 in that matrix equation, in the first matrix equation, the I2 on the right hand side, we can replace that I2 with V2 on Z, because that's what it is, V2 on Z, right? So then we have the equation V1 equals AV2 from that matrix, second matrix equation. And we have I1 equal to 1 on A times V2 on Z. We have that equation. So now we can write using these two equations, V1 equal to AV2 and I1 equal to V2 on AZ. If we now find the ratio of V1 to I1, we have V1 I1 equals A squared Z, because V2's cancel on the right hand side when we divide. So what does this tell us? This tells us V2 on I2 is Z. That's the impedance that you connect to the secondary. Now V1 on I1, that's the impedance seen by the primary, right? The ratio of the voltage V1 to I1 is what the primary sees. And V1 on I1 is A squared Z. So it's saying a different impedance to what the secondary is saying. Secondary is saying Z because V2 on I2 is Z. V1 on I1 is in fact A squared Z. So what that tells us, if you have an impedance Z on the secondary, we can actually bring it to the primary by multiplying that Z by turns ratio squared, by multiplying by A squared. That's what that is telling us. So let's look at an example. A single phase power system consists of a 480 volt 60 hertz generator. So 480 volts is the source voltage that is connected to the primary terminal of the transformer, supplying a load, Z load 4 plus J3, that's the load Z, right, connected to the secondary terminal of the transformer. Through a transmission line impedance, Z line equal to 0.18 plus J 0.24. So this is what we have. we have actually two transformers, right? We have a transformer on the left and another transformer on the right? And we have a transmission line connecting the two. So the transformer on the left is a step-up transformer, right? That's what you do when you generate electricity, you step it up. And then you connect to a transmission line, right? And then you step it down at the residential side. So you go from 10 to 1 on the receiving side, right? So the question that, and the impedance of the, so it's a short transmission line, so we only have a series series impedance, right? So it's a short transmission line. So what do we have? If the power system is exactly as described above, see figure A on the next page, what is the voltage of the load and what is the power loss of the transmission line? So if we were to connect without the transformers, without stepping up and stepping down the voltage, this top figure is what we have. If we were to step up and step down, it's the bottom figure that we have. So we want, for these two cases, we want to calculate what's the I squared R loss in the transmission line. What is the power loss? You want to minimize the loss in the transmission line. So obviously by stepping up the voltage and stepping down at the receiving end, we know the power loss is going to be less, and then we're going to see the numbers for that in this example. So for the first case, for circuit A, the top circuit, what is the line current is simply the voltage, right? The voltage, source voltage divided by the entire impedance, the line impedance and the load, right? We have the line current as 90.8, lagging current minus 37.8, right? Taking the source voltage as our reference. So the current is lagging. That makes sense because the entire load is inductive, right? Transmission line and the load is inductive, so the current lags. The load voltage, how do you find the load voltage? You take the line current, what flows in the line, multiplied by the load impedance, right? Multiplied by the load impedance, you get the load voltage. So the load voltage is something like 454 and angle minus 0.9. So you can see the sending end voltage is 480. Receiving end, at the receiving end it's 452. So there is a voltage drop as current travels through the transmission line. And if you were to calculate the power loss, it's the magnitude of the current squared, right? The magnitude of the current, line current squared. So the magnitude of the line current is 90.8, right? Because there are various ways to calculate the active power in an impedance, right? We can take the magnitude of the current square times R because that current is flowing through that resistor, yeah, in the series resistor. We can calculate it that way. VI star is another method. VI cos theta is another method. VI star, the real part. These three ways to calculate it. So make sure that you know all three ways to do it, yeah, calculate it. So in this case, we simply take the magnitude of line current squared times R, and we calculate the power loss in the line to be 1,484 watts. That's how much power is lost. If we were to transmit power using circuit A on the top. Now let's see what happens when you use circuit B on the bottom, where we step up the voltage and step down the voltage. So, so here, yeah. All right. So what we do in this case, we take this impedance on the right hand side, right? This impedance here on the right. We reflect it from the secondary side to the primary side, right? So when we do that, what do? We take the turns ratio squared and multiplied by that impedance. So the turns ratio is N1 on N2. So the turns ratio, the relevant turns ratio is 10, N1 is 10, N2 is 1, right? So turns ratio squared is 100, right? So this value gets multiplied by 100, and then we can get rid of this part, right? And then connect 400 plus J300 here, right? Yeah. And then the next thing is when we reflect these impedances to this side, right? Again, we take turns ratio squared and multiply it. So if I take turns ratio squared, turns ratio is N1 on N2, which is 1 on 10, right? So turns ratio square is 1 on 100. So if I multiply this by 1 on 100, this will become 0.0018, right? This will become 0.0024. This will become 4, and this will become 3. Yeah? So we end up with this circuit, 4 and 3 and 0.0018 and 0.0024, right? That's the circuit we have with the two transformers. Now we can calculate the current. The current is going to be this total impedance divided by the voltage, which we will get this figure, this value for the line current. Right? So here, so that's, we can calculate this current, right? These numbers here refers to something else, but doesn't matter, right? We can calculate this current, yeah? And once you calculate this current, this I, I'm not going to do the calculation here. You can do the calculation. It's simply this impedance value, this voltage divided by the impedance values. And then you want to find out the line loss. It will be the magnitude of this current squared times this value. Yeah, would be the loss. And that loss will simply come out to be 16.7 watts. So compare that 16.7 watts to 1484 watts, which is a situation that we have when we don't have the step-up transformer and step-down transformer. We knew the value is going to be less, but these are some numbers that demonstrate that. Yeah. So you can do the calculations. You can follow the calculations here, but I just outline how to go about doing this, how to go about understanding what's happening here. It's about taking the transformers from the secondary, reflecting it to the primary, and you continue that, and then you end up with this circuit, and then you can calculate the current, right? And this current here that you calculate is the current that flows in the generator, right? Once you know the current that flows in the generator, which is this current here, then you want to find exactly what flows there, you can find it. Because you know I1 on I2 is equal to N2 on N1, right? And once you know this current, and you want to find out what that current is, again you use that formula to calculate it. And that's what we are doing down here and here, right? Yeah? Because the current that you calculate in this circuit, because you have reflected, keep reflecting from the secondary to the primary back, and then back to the primary again, right? You're reflecting from the secondary to the primary of that transform on the right, and then again that's essentially the secondary of this transform on the left. Again, you reflect it back to the primary of the transform on the left, right? You end up with this circuit, right? And then the current that you compute is actually this current here, because you kept reflecting it from right to left. You keep getting the generator current. And then if you really want to know what the current on the transmission line, the exact values, then you know this current, therefore you can find that current using the turns ratio, right? You know that I1 on I2 is equal to N2 on N1. the inverse of the turns ratio. All right, so that's a very simple calculation. That's the ideal transformer, right? So we talked about reflecting impedances back into impedance values from the secondary back into the primary by using the turns ratio squared. So you know that. We've looked at an example there. We've looked at why it is advantageous to step up transformers before transmitting power and then stepping down after the transmission line before consuming. We can minimize the I squared R losses. All right, so that's the ideal transformer. Should be fairly straightforward. You should be able to follow the lecture notes and the calculations that are done there. And here we looked at the real world transformer. So it's a picture of a real world transformer here. So there are a few components to it. We've numbered and I've labeled it and also given some brief descriptions here. You can read that, right? So just briefly, it has a transformer tank, which is this number 1, where you will find the primary coil and the secondary coil enclosed in this tank. High voltage bushing and low voltage bushing. So that's providing some insulation to the primary coil and the secondary coil, right? Then there are some cooling cooling fins and radiators to bring down the temperature because there are I squared R losses. There's heat generated, so you need to cool it. There are some fans, cooling fans that will be activated if the temperature is quite high, which is number 4 on the figure. And there is a tank there to, preserve some oil. Then there is the ground terminal, which is number 7. There is some drain valve, so you can drain and refill. And then there's a temperature sensor, pressure gauges, and surge arresters, etc., to protect the transformer from voltage surges and so on, right? Protect from lightning. So those descriptions are given here. You can go and read for more about it there. Right. So with real transformers in our analysis, we will assume that there is winding resistance. So we're no longer going to assume the winding resistance is 0. We will assume we will not assume the core permeability is infinite. We will assume it is finite. So the reluctance won't be 0, right? Reluctance will be some value. The magnetic flux is not entirely confined to the core. Previously, we assumed there is no leakage flux entirely confined to the core. So here we will assume there is some leakage flux. We will also assume there are some losses. There are active and reactive power losses in the core of the transformer. So we're not going to have simplified assumptions like in the ideal transformer case. All right. So transformer core losses, which are also called eddy current losses, right, are due to eddy currents that are flowing in the core. So when changing flux links with core itself, it induces EMF in the core, which in turn sets up circulating currents called eddy currents. So in the core of the transformer, we observe circulating currents, which are called eddy currents, and that gives rise to some I squared R losses in the core, right? You can minimize these losses, these eddy current losses, by reducing the magnitude of eddy currents. Obviously, you can minimize the losses by laminating the core material. By laminating, it's possible to, so it has to do with some construction. So the laminated core is drawn here, you can see, and that is to minimize the eddy current losses. And also another way to minimize that loss would be to use magnetic material having higher resistivity like silicon and steel, so that the currents are minimized, the eddy currents are minimized. Another type of losses in the core, so there are two types of losses in the core. One is the eddy current losses, which we just mentioned, and the other type of loss is the hysteresis loss. Hysteresis loss has got to do with the shape of the BH curve. B lags H. H is the magnetizing force and B is the flux density. So BH curve for a core, B lags H and has this shape, and the area enclosed by this hysteresis curve, you can see the BH curve. So as H increases, it takes one path, and as you decrease H, then it takes a different path. So the mapping for B to H is not one-to-one. It has this shape that is shown in this figure, and the area inside enclosed in that hysteresis curve is what is the hysteresis loss. So then that is some kind of a loss. So there are two types of losses in the transformer. One is the eddy current losses, and the other one is hysteresis loss, which has to be taken into account in a model for a transformer. So the transformer, again here you can see the magnetic flux in the dotted lines. Not all the flux is confined to the core. You can see some flux is leaking out of the core. So this is the leakage flux. All right, so let's start it. Let's start the projector. All right, no problem. So not all the flux is confined to the core. You can see there is some leakage, as I highlighted in yellow. So that needs to be taken into account in developing a model for a real transformer. All right, so let's try to develop a model for a real transformer. So the magnetomotive force, the MMF, is N1 I1 minus N2 I2. We talked about that. Previously it was equal to 0 because the reluctance was 0. In this case, reluctance is not 0. We're no longer going to assume it's 0. So it's a reluctance times the flux in the core, phi c, right? That's and the net non-zero MMF is given by that equation. And if you take this equation and now divide both sides by N1 and take that minus N2 I2 term to the right hand side, you have I1 equals the reluctance times the phi c, right, flux in the core divided by N1 plus then N2 divided by N1 times I2, right? So we have this equation. So now we can see we are quite familiar with this part of the equation. That comes from the ideal transformer. N2 I1 is equal to N2 on N1 times I2. We are familiar with that, right? I1 on I2 is equal to N2 on N1. So this is I1 here must equal to N2 on N1 I2. That's from the ideal transform equation. But now we have this additional term, reluctance times the phi c divided by N1. And then we can actually call this the magnetizing current. We can just define it. We can call it, give it that name, magnetizing current. So I1 is in fact equal to Im plus N2 on N1 I2. For the ideal transformer case, this I2 didn't exist. There wasn't there, right? Okay. So now we can see, right? See, the ideal transformer was just this bit here, right? That's the ideal transformer, and this current here was simply I1, right? Yeah. But now I1 is made up of two components. I1 is made up of some current, right? Some current plus this current. So you can see this shunt branch accounts for this Im, right? And this is the part that flows in the ideal transformer component. So this is the ideal transformer component, right? Yeah. And this is the other part, the second part that we introduced is the part that will flow in a shunt branch, right? So if we now consider this circuit, this is the equivalent circuit for a transformer, a real transformer without assuming ideal scenario, ideal condition. So we can see that X1 and X2, these terms, they relate to leakage flux because there is some flux leakage, so which is accounted by those reactance terms, those inductors, right? Leakage flux, X1 and X2. Resistors R1 and R2 represent the winding resistance in the primary and the secondary. Right? Winding resistance in primary and secondary. We know that in the core of the transformer there is some hysteresis and eddy currents, right, which was not taken into account in the ideal transformer, right? So this parameter GC, because there is some active power loss, GC represents, or some resistance or conductance represents the eddy current loss and the hysteresis loss, right? And the non-zero, the reluctance, non-zero reluctance, which provided the magnetizing current, right, which is related to the flux, again is represented by an inductor in the shunt branch, which is this part here. Right? So it's an inductor that represents the non-zero reluctance. So BM accounts for the effect of finite permeability. Permeability is not infinite, it's finite, so the reluctance is non-zero. Right? And that gave rise to this term here. This term. Right? So we have this model for a transformer now. We have winding resistance, we have some reactances, right, X1 and X2. We have winding resistance R1 and R2. We have core losses represented by the parameter GC, right, some resistor value in the shunt, and magnetizing current represented by an inductor which has value Bn. So that's the equivalent circuit for a non-ideal transformer. All right. So now we can also see that this current that is flowing in this branch is actually N2 on N1 times I2, which we have seen in the ideal transformer model. Right? We have seen that. So the current that flows on the secondary is I2, right? In the secondary terminal, current that flows in the primary terminal is I1, which is just not only that term, but also made up of this term and this term. One current representing the eddy current and hysteresis losses, the other current, magnetizing current, representing the finite reluctance. Okay. N1 is the turns in the primary, N2 is the turns in the secondary, E1 is the induced voltage in the primary, E2 is the induced voltage in the secondary, V2 is the secondary terminal voltage, V1 is the primary terminal voltage. So we know what all the terms, what they mean. We need to be clear on that. Yeah. All right. So here again, it's the same thing. What is happened here? We have this R2 and X2 on the secondary side, we can reflect that to the primary. We can bring it to the primary if we want, right? And if you do that, we need to multiply by turns ratio squared. And here is the turns ratio squared, we multiply it, right? So R2 and X2 has been taken from the secondary side to the primary side now, right? And then if this current that IE that is flowing in the shunt branch, if that is small, we can make a further approximation. In fact, we can shift it to that part, the shunt branch to the left to simplify calculations, which we're going to do. So we have now shifted that shunt branch to the left so that these resistors and reactances can be added with these guys. So this part here now moves here. Right? Moves there. Just a simplification to make our calculations easier. So now we have this DV equivalent circuit. So we have a shunt branch, so we still have this GC and BM, right? We have taken the resistance, winding resistances, and then we've added winding resistance in the primary and winding resistance in the secondary. Of course, the winding resistance secondary we multiplied by turns ratio square and we added to the primary winding resistance, right? So this is what we have, right? And we've done the same thing with the reactances, right? And A is the turns ratio. So this is the equivalent circuit referred to the primary side. We can also have the equivalent circuit referred to the secondary side, in which case we will be adjusting this R1 term. We'll be, instead of multiplying by turns ratio squared the value of R2, we'll be dividing by turns ratio squared the primary resistance, and then it will reflect the primary winding resistance to the secondary. And we'll then do the same thing for this and this as well, right? Because those are values in the primary. If we're going to take it to the secondary, then we have to divide by turns ratio squared. Now the circuit, as you see here, is the equivalent circuit of the transformer referred to the primary side. Is referred to the primary side. Yeah. Right. So what we want to talk about now is how do we determine the parameters of the equivalent circuit of the transformer? How do we determine the parameters? Because we know there is R1, R2, X1, X2, GC and BM. Those are parameters of the transformer. We talked about what they mean. How do we going to determine that? So the way to determine that is to do an open circuit test and a short circuit test. The open circuit test will tell us the parameters on the shunt branch, and the short circuit test will tell us the parameters on the series branch, right? And you will understand why. So the open circuit test, we obviously open circuit the secondary side of the transformer, so we don't connect any load. So the secondary terminal is an open circuit. We make a power measurement, and also we make a current measurement and a voltage measurement. So we make three measurements. We make a voltage measurements. So we make the voltage at the terminal of the primary side of the transformer, voltage measurement. We make a current measurement, right? Current in the primary winding. And we make a active power, how much power is consumed, active power measurement. We make three measurements. The secondary is an open circuit. Now you can actually kind of see, right? You can kind of imagine this is the equivalent circuit of the transformer, right? So we are connecting something to the primary side. We're connecting a source to the primary side, right? We have the right hand side open circuit. We don't have no load. So then you can see with this, you're just going to you're going to look at the shunt branch, isn't it? You're going to get information about the shunt branch, yeah, with the open circuit test. You can clearly see that. We're going to look at that in detail. Now the short circuit test, you can see the secondary. We are going to short circuit the secondary, right? And if we assume that the amount of current that's going to flow in the shunt branch when we short circuit is small, because most of the current is going to flow through the short circuit, right? We are then going to look at the series elements. Yeah? We're not, because we are open circuit test will already give us information about the shunt branch. Short circuit element, test will then tell us about the series branch. Yeah? We're going to look at that in detail. All right. So, here it is. We're making 3 measurements, open circuit test. We are measuring the voltage, a voltage that is appearing across the shunt branch, right? We are going to measure the current. We are going to measure the current that, the only current that flows is in the shunt branch. So we're going to measure the current in the shunt branch, right? Which is this current here. Which is this current here, right? That's going to flow in the shunt branch. We're going to measure the voltage across the shunt branch, right? And we have the conductance. We have the admittance. We represent the conductance and susceptance, right? Why do we represent the shunt branch as conductance and susceptance? Do you recall from my first lecture? Because when you have elements in parallel, it's convenient for us to think about conductance and susceptance, because you can just simply add them, and then that's the admittance, right? That's the admittance, right? That's the admittance. So we are going to, so the admittance Y is simply GC minus GBM, right? Actually, I should write plus GBM. That minus is actually part of BM. I'll leave it like that, but it doesn't matter, right? But you understand that. So, now, if I write it in polar form, right? If I write it in polar form, right? If I think of this, I mean, I could still think of this as a impedance, right? Because it doesn't, I can even think of it as an impedance as well. I could think of it as Z. Z is 1 on Y, right? Yeah? Now, if it's Z, there is a magnitude and an angle, right? Angle is theta, if it's an impedance. If it's an admittance, admittance is 1 on Z, right? So then it still has a magnitude, and the angle is the negative of that, negative theta. So that's why I put negative theta, right? Okay? Now, if I have, so here what I do is, if I calculate, like I have the magnitude of the current, magnitude of the voltage, right? If I take the ratio of the magnitude of the current and magnitude of the voltage, I will get the magnitude of the admittance. Magnitude of Y. I get the magnitude of Y. Current, magnitude of current or magnitude of voltage is the magnitude of the admittance, right? Now, we have a power measurements, right? The active power is the magnitude of the voltage, magnitude of the current times cos theta, right? Cos theta. So cos theta must equal the power, active power, or the magnitude of the voltage, magnitude of current. So I have theta, right? So now I have the angle of the admittance, because the negative value of that is the angle of the admittance, right? So I know the admittance now. With the 2 tests, with the 3 measurements, with the open circuit test, with the 3 measurements that I've done, I have the magnitude of the admittance, I have the angle, because that theta that I compute, if I negate that, that's the angle of the admittance. Now, this is in polar form, right? I can then write it in Cartesian form, right? I can change the polar form into Cartesian. Then the real part is GC and the imaginary part is BM. Right? So GC and BM I know. If you want to convert it to a resistor, 1 on GC is the resistor, inductor, invert the 1 on BM and you get the reactance. Right? If you want to convert it. So that's the open circuit test. So I think it's important to understand, but I want you to think a little bit more. When you calculate the angle theta, cos inverse, right? why I need to negate that here to get the angle of the admittance. Right? I would like you to think a little bit about that. I'll give you a hint. All right. So think about impedance Z, right? Think about a voltage that appears across the Z. Think about the current that flows into the Z. Okay? So we have, and we'll take the voltage as our reference. So we'll say V angle 0 is the voltage that appears across the Z. Okay? Then the impedance Z has an angle positive theta, right? Z, magnitude Z, positive theta. Then what is the current? The current is going to be the negative I minus theta, right? Yeah? I minus theta. Right? I minus theta. Because then when I multiply I by Z, Z has a plus theta, current has a minus theta, plus theta and minus theta will give me 0, right? VI cos theta, right? So when although I represented this like this, that's still an impedance, right? So when I get that angle theta, right, cos theta, right? If this reference is 0, then yeah, I would like you to think a little bit on that, like that, so that you fully understand when you compute that theta, and then you negate that, you put it there, and the magnitude of the y you compute in a certain way. I want you to be a little bit clear on that. So can you think about that? Think about that. There are some examples. So we look at the example. It'll be a bit clear, but I would want you to think a bit on that. Yeah? So let's talk about the short circuit test. So this is a short circuit. Again, we are going to make the same 3 measurements, right? The power measurements, voltage measurements, the current measurement. So when you make the short circuit, all the current is going to flow through the series branch and nothing on the shunt, or very little, which we can ignore. So here, so we have the ratio of the voltage to current, and that's going to be the magnitude of Z, because I'm going to think of this as Z, right? Magnitude of Z. Yeah? And then, if I take the ratio of the voltage to current, if I do this angle, right, VI cos theta, right, because VI cos theta is power, so we can calculate the theta, and that theta is just the Z theta, right? But in the previous case, because we are thinking of admittance, we had to actually negate that theta. But here we don't, because that's that theta there, right? Admittance is 1 on that, which is minus theta. That's why the previous case was minus. Is all good? Yeah. All right. So let's look at an example, right? So it'll clarify what we discussed on the 2 open circuit test and the short circuit test. The equivalent circuit impedance of a 20 kilovolt amp, so that's the rated power, 20 kilovolt amp. 8,240 volts. So 8,000 is the rated voltage on the primary. 240 is the rated voltage on the secondary. So the turns ratio is going to be what? This 8,000 on 240 is the turns ratio. Right? 60S transformer are to be determined, the equivalent circuit impedances. So we need to find the parameters for this equivalent circuit. The open circuit test and the short circuit tests were performed on the primary side of the transformer, and the following data are taken. So the open circuit voltage is 8,000. Open circuit current is 0.214 amps. Open circuit, for the open circuit test, the power measurement is 4,000 watts. It's 3 tests that we are doing. So let's focus on that, and then we'll come back to the short circuit, same measurements for the short circuit, voltage, current, and power measurements. So from the power measurement for the open circuit, we can calculate the power factor, which is cos theta, right? It's a lagging power factor, right? Current lags the voltage. Why? Because it's an inductive load, where inductive shunt branch we are thinking, yeah. So it's obviously lagging. And the admittance is simply the current over voltage is the magnitude, and the negative value of the angle that you get is the angle. That's it. And then you convert it to Cartesian form, and that's GC and that's BM, right? In fact, the BM should have the negative value attached to that. And if you want to convert it to an inductor value, then it's 1 on minus BM, which becomes a positive value. It's a minor thing, yeah? We talked about that in the first lecture. And the same thing, we have GC. If you invert that, you will get the resistance. Disconnecting. It will be so much easier if everybody is here, isn't it? Because with this, I can't now move from here. I have to stand here and talk. Yeah, because I have several mics. I got this mic. I got the mic of the computer. Anyway, let's give it a minute. There is no internet connection. I think I'm just going to continue. Yeah, there's no internet connection. Okay. Unfortunately, there is no internet connection, but I'm going to continue like this. Yeah. All right. If that connects, we'll go back to that. But yeah. All right. So we have we computed the parameters of the shunt branch. Yeah. We computed the parameters of the shunt branch. Now, let's go back to the short circuit test. Again, we have the voltage, current, and power measurement, right? So, for the short circuit test, again, we compute the power factor, because we know the power, we know the voltage, we know the current measurement, power factor. We find the angle theta, right? It's a lagging power factor, right? Again, because it's inductive, the shunt, the series branch. Then we can find that impedance, the series impedance by, this is wrong, it should be, change it, it should be the voltage on current, right? Not, and it's not the exciting admittance, it's a series impedance. So change it, it's the voltage on current cos inverse power factor, which is that, and then in polar form, and if you turn it to Cartesian form, you have the resistance in the series branch and the reactance in the series branch. That's it. It's simple as that. So here are the values. That is the transform equivalent circuit referred to the primary side, because the measurements are taken on the primary side. Right? Measurements are taken on the primary side. So, now I will go through this and then finish off the lecture here, and then again I'll restart with this because this is an important part, so you will get to hear it twice. The other guys will, well, they will have to listen to the recorded message if they want to listen twice. Right? It's beyond my control anyway. So here, all right, so this is the equivalent circuit for the transformer. Equivalent circuit for the transformer. Now, we have the primary side, primary terminal on the left hand side. We have a shunt branch, we have the series resistance and the reactance, and the secondary terminal on the right, and then we can connect a load there, right? We can connect a load to the secondary terminal, which is on the right. Now, what we are trying to do is to draw the phasor diagram for this. So when you're drawing the phasor diagram for this, again, we can choose our reference voltage. Yeah? And we are going to choose the voltage across the load on the right as our reference. Right? And notice that the voltage on the right, because this is the transformer referred to the primary side, so secondary voltage is Vs, but when you take that voltage and refer it to the primary side, it's A times Vs, right? Because you know V1 on V2 is equal to A. It's A times Vs. So if you take anything, any voltage, if you take from the primary to the secondary to the primary, you need to multiply by turns ratio. The impedances by turns ratio squared. Currents you divide by turns ratio. Secondary currents if you're taking it to the primary. So A times Vs is there for that reason, right? Now that A times Vs, we are going to take that as our reference. So you can see on the phasor diagram, A times Vs is horizontal, right? A times Vs is horizontal. Now the current that flows through that, because it's Is flows through that, but current, if I take it to the primary, I need to divide by turns ratio. So that's why I have Is on A, right? Now that we have drawn it as lagging, right? But it can be leading as well, but in this case, I've drawn it as lagging because the load is inductive. We assume it's inductive. If it's not inductive, if it's capacitive, then it will be leading, right? We assume it's inductive. But if it's leading, again, it doesn't matter. You can still redraw. You can draw the phasor diagram. We will look at examples of that in the future. So Is on A is lagging. So AVS, no problem. That's our reference. Is on A is lagging. And what determines that? It will be determined by the power factor of the load. So it's a lagging power factor. This equation what we are drawing, it will depend on the load, power factor of the load. So then, if Is on A is like that, then the voltage drop across the series resistance will be parallel to that current, right? Voltage drop has to be parallel to that. Across the resistor has to be parallel to that, Is on A. Then voltage drop across the series inductance will be 90 degrees ahead, right? So you have that line there, the phasor, right, ahead. So you have Is on A. So this is the voltage drop across the series resistance, right, which is parallel to the secondary current, and the voltage drop across the series inductance is 90 degrees perpendicular to that. Yeah. So now if I sum those three vectors, we will get Vp, which is the primary voltage. Right? Vp is the primary voltage. Now, Vp is the primary voltage, and then this current IC, which flows through RC on the shunt branch, has to be parallel to Vp, right? And the current that flows through XM has to be 90 degrees behind, right? Because it's an inductor, right? Current lags the voltage in an inductor, 90 degrees behind. And if I add IC to IM, I'll get I0, which is the current that flows here, right? And if I add IO to IS on A, I will get IP, which is that. Right? So, you should be able to draw this phasor diagram without having to look at it. So, you should know the equivalent circuit for a transformer, right? And you should be able to draw this circuit without having to look. So you don't have, you can have a clean sheet of paper, blank clean sheet of paper, a pen, draw the equivalent circuit for the transformer, and draw the phasor diagram. Then without having to look at anything, then you will know, maybe you understood something of this lecture. Maybe you did. So try it out. When you go home, just get a blank sheet of paper and regenerate that. And we'll see you. We'll stop here for today, and we'll see you again next week.